So to kick us off, we have Abhi, who's a professor at Northeastern and a researcher at Google. And this transitions pretty well from the last talk because we just heard about Ligatron, and Abhi's going to talk about how they use Ligero, which is shared in common with the previous talk.
Thank you, Kathy, but it's Northeastern. I know in Western Eastern, it's like a hard thing, but anyway, thank you for the introduction. So the romance of zero knowledge. I'm going to ground it with a very practical problem, which is many websites today, they actually require you to take your driver's license, take a photo of it and upload it to basically get past that one step in that website. That's a really terrible thing right now because you know that once that website has been breached, which most websites gets breached, your data is basically gone and it's somewhere on the web allowed for someone to basically download. We need to essentially fix that problem. Fortunately, there are at least five states, and all 45 others are going to do this. They're going to issue you digital signatures on your driver's license. Now, what can you do with that? You can actually make zero-knowledge proofs about documents that are issued by states like DMVs. This talk is about grounding ZK for identity. And the first thing is that ZK for identity actually has a different constraint than all of the academic literature. Most of the literature on ZK for the last 15 years is talking about this notion of succinctness. But actually in this problem, ZK for identity, it's the opposite. You actually have a very small phone that has to prove a statement about a small statement to a very large web server. So actually all of the literature on succinctness is not really relevant. We actually just need a NARC for this particular application. And the most relevant factor is the prover time. And of course, the proof has to be small enough to be practical for this type of thing. The second major constraint is that it would be very arrogant for cryptographers to essentially ignore all of the other people working on identity. There's actually been a huge community of people who standardize identity formats. And there are a lot of essentially corner cases and little sort of very complex situations that they have worked through already by formalizing things like MDOC and JSON web tokens, et cetera. And we should actually sort of build on top of that. Additionally, human coordination is probably one of the hardest things to achieve, as Europe and US is like sort of showing right now on CNN. So if we want to minimize coordination, we should probably not rely on the existence of trusted setup parameters that essentially all 27 European nations and all 50 states essentially agree upon. Finally, we should acknowledge the limitation that issuers are very limited here. We should not put the DMV in the middle of every internet login. And that means they shouldn't be online for every login. They shouldn't also be required to do the work that's proportional to every internet login. So I think that's a mistake for large-scale deployment of this type of thing. So we should look for solutions that have none of these particular problems. And fortunately, the right ZK system can actually solve all of these type of things. And in fact, the rest of this session is going to give you 3 different approaches. I want to give you my particular approach and my opinion on what I think are the important relevant factors. So we're actually going to use the second oldest recipe for zero knowledge. So this predates many of these type of things. This very famous paper essentially says if you have an IP, you run the IP to get a transcript for that. You commit to that transcript, and then you use a special zero-knowledge system just to prove that the commitment contains a transcript and the IP verifier on that transcript would accept. That is the oldest recipe for proving zero-knowledge. Everything provable is provable in zero-knowledge. And the only thing that remains is picking these 3 primitives. And our approach has made an opinionated selection. The first one is sum check or layered sum check or GKR. And importantly, the prover in that proof system runs in linear time. And I'll show you with the receipts with data about how fast our system works. This is a very important critical factor for making this work on phones. The second choice I made was Ligero for the commitment and ZK system. Ligero is very easy to implement, and it also follows from the MPC in the head paradigm, which is also older than many of the other Sigma protocol-based systems. So both of these things are well tested. There's in fact a formalized proof of sum check in Isabel. So the approach that we're planning to use is, again, to run Ligero on the output of a layered sum check protocol. And my point is that doing this way actually for problems of this particular size, in this case, actually is faster than running just pure Ligero. And the next 2 talks are going to use a different type of approach. All of them are going to use Spartan ZK, which is also another sum check-based system, but it's based on R1CS, and I want to argue that essentially a layered sum check actually has an advantage over an R1CS, which is actually a flattened version of a circuit. So why is that? Let me try to give you a picture proof in this short time here. Ligero and every other system which doesn't use this trick of first committing to an IP actually has to commit to every wire of the output of a circuit. Now that's a little bit of a lie. You actually only commit to the multiplications, but for the multiplications you have to commit to the two inputs and the output, which is roughly this. That's why this diagram is roughly accurate. In contrast, if you do my recipe, which is Ligero on a layered sum check, all you need to do is commit to the input to this circuit and the sum check transcript, which, if you follow the literature, essentially that is much, much smaller than the number of wires in the circuit. Okay? And in fact, the commitment in these schemes, all of these modern proof systems use what's called the number theoretic transform. That's an n log n algorithm, and essentially to interpolate polynomials. And that is a bottleneck because the commitment is essentially running NTTs on all of the elements in there. So if you can reduce the amount of data that you commit to, you can actually get beyond the n log n boundary and in fact make the proof system faster. And that all of our empirical evidence essentially for this problem size shows that this works out. So speaking of bottlenecks, one of the other prior bottlenecks to making ZK for legacy credential systems work is essentially making proofs about legacy signature schemes like ECDSA. So prior work that had done this, for example, that work, actually had to do this very laborious thing, which is simulating the math of FQ and FP. Those are related to the particular curve, the ECDSA that we're talking about. They have to simulate that in whatever field they're doing their ZK proof in. And you might ask, why don't they do their ZK proof in exactly the field that the elliptic curve is based on? So P256 is a standardized elliptic curve in the United States. And unfortunately, if you look at the P256 finite field, it does not have roots of unity. So if you know how to look for whether something has roots of unity, that right there equation is a picture proof of this doesn't have it. However, the extension field for this P256 does. So in fact, that was one of our second big tricks, which is if we do the NTT in the extension field, keeping in mind that all of the witness variables are in essentially the base field, and so we actually get a lot of efficiency from that, we can actually run NTTs on exactly the right field. And the other two talks in this session will talk about other methods for essentially achieving this, but I think this is one of the better ones. And it shows you that if you do the right field math, you can actually get an arithmetization of ECDSA verification with roughly 50,000 terms. And again, let me point out this particular fact right there, right? If our system only needs to commit to 1,000 inputs to give a proof about this, and if you just use R1CS or any other system, and you'll see in future talks exactly how many wires they need, again, there's a 50x reduction in the amount of commitment that you need to do if you actually use our recipe. Okay, so what does that mean? Ultimately, we can do a zero-knowledge proof of knowledge for an ECDSA signature in about 60 milliseconds on a single-threaded x86, and we do all of our tests in Pixel as well, and it takes about 80 milliseconds there. These are some numbers from other systems. I think the fifth talk is going to give an updated value, but still, it's about 4 or 5 times slower than our recipe. I also want to give you information about how our system works for SHA. Basically, we can run a proof of pre-image of a SHA with our system in about 11 milliseconds. And if you put that together, okay, so if you put that together, what that means is if you have ECDSA and SHA and parsing, something that I haven't really talked about, but that's in our paper that's on ePrint, you can actually start applying zero knowledge to a legacy protocol like MDOC. MDOC is the ISO protocol for mobile driver's licenses. And as Anya basically mentioned, in the status quo, a relying party will basically say, hey, I want to check if you're over 18. It'll send you this information. And in the current protocol, you essentially send the entire MDOC as well as a pre-image for the salted hash for the attribute you want to show and some signature on a liveness check. And all of this information essentially proves the statement, but it also gives you a tracking cookie. So it gives a relying party a tracking cookie for you. These are the 5 steps that the relying party would actually do to verify this type of thing. And so you can put that into our compiler, all 5 of these steps, and essentially ask for a zero-knowledge statement for all of these particular equations right here. And I'm not going to go through exactly what they are, but I will tell you that the most costly part of it is essentially computing the SHA of the very large mobile driver's license document. And on a Pixel phone, it runs in about 1.2 seconds with a verification time of about 0.6 seconds. And that is actually efficient enough to actually run when user trials for people trying to log in instead of taking a picture of your driver's license and throwing away your data, which you would eventually do if you do that. This type of thing actually is a very suitable solution, and we've implemented it. We can also support something like credential revocation. There's various ways to basically to do that. We can also support pseudonyms. Again, when you have a circuit-based proof system, you can actually add these extra features as they come along very easily, just by adding a little bit of information to the circuit. I also want to say that we can support JWTs, so you can support both MDOCs and this JSON Web Token format, or SDJWT, which is another popular identity format. We have circuits for this as well. And the last thing I wanted to comment about is the fiat Shamir attack. So Ron Rothblum, Yael yesterday essentially mentioned something about this, and Ron Rothblum and his co-authors have a very interesting attack on fiat Shamir for certain kinds of GKR protocols, right? And Yael spoke about them, but I want to tell you why our system is very different. Remember, the first important thing is that we don't really care about the theoretical notion of succinctness. Now, of course, it is verifier or succinct, as kind of our numbers kind of show, but if we don't care about exactly meeting the technical definition of that, we can actually do some very simple countermeasures. One of them is that we can essentially pick the random oracle function after we have set the circuit. And that's one of the powers that we actually have in our system. And we can actually set the random oracle function to be more complex than F, thus ruling out the possibility of the attack that Ron had pointed out essentially relies on the protocol evaluating or predicting the next output of the random oracle. And by carefully orchestrating things and using this type of assumption, you can essentially eliminate that. Another important thing is that nobody really uses sumcheck to compute a function. We actually all use it to verify. And that's a very subtle distinction that essentially eliminates the type of attacks that Ron has at least currently has. Now, of course, our goal as cryptographers is to have a more formal understanding of why fiat Shamir basically works, but at least all of the ZK proposals out there use fiat Shamir in one way or another, and there should be some good reasons like these for why these systems don't apply to ours. Now, our open source code will be available, and I wanted to leave about 2 or 3 minutes for questions. I went through my material fast, so I'm happy to go back. Go ahead.
Awesome.
This P52, this P5256 trick is pretty cool. Is that compatible with? Can they be made compatible with pairings? The other and one other observation. You mentioned something about trusted setups. There was a nice talk yesterday that pointed out that trusted setups are not at all a problem for governments because we do these things all the time for DNSSEC. It's not, but also it can be used a bit like a certificate. And I wanted to point out that when you use GROS16, you can use re-randomization, so you get things like anonymous credentials where the prover time is tens of scalar multiplications.
Okay, so you asked like 3 questions, but let me go ahead and say the next talk is going to talk about re-randomizing GROS16. The problem with GROS16 is you still need about a gigabyte on your cell phone, and with 400 million European phones, it's hard to say that we should spend about 400 terabytes. You need a very large string. Whether you want to argue that it's 50 megabytes or 100, we all have to agree on a very large parameter, and that doesn't fit on. Google, for example, won't let us deploy something which puts 50 or 100 megabytes on the phone. The other questions you had about, I can hand them all offline. I don't remember them. So ask one, please, and we only have 2 minutes.
So just clarifying, the 1.3 seconds, is that every single time you would prove to the website? Do they give a new nonce and then you have to do a proof with respect to that fresh nonce?
So yes, I have a video to show you essentially, but every time you use this credential, it requires you to use for device binding, it requires you to do a biometric check. You have to actually unlock your secure enclave. And so that requires the thumbprint. So every MDL show, even without zero knowledge, requires a human interaction of a thumbprint. That's why 1 second extra for zero knowledge isn't relevant in this type of user flow, because it can be hidden even though we don't hide it. But the point is a human action has to be taken, which is on the order of seconds anyway. And that's required for the security of device binding.
Last question.
Could you share again what the size of the proof is and the verifier time? And maybe
The size is roughly 400 kilobytes, and the verification time is about 0.6 seconds. And that is because we use SHA-256. That's the post-quantum assumption that we use. If we use elliptic curves, we can use a smaller commitment and actually change those sizes as well.
Okay.
Awesome. Thanks again, Abhi.